So the topic I will be telling about today is kind of an interface between traditional many-body theory and we will say something which is related to data mining in the sense of very advanced statistical analysis. And the entry level for this discussion is actually an experimental fact. Okay? And here what I show in this slide are platforms that most of us are accustomed to, so trapped ions, atoms in optical lattices, atoms in tweezers, or circuit QED architectures. And there is one element in common that all these systems have, despite their differences, is that in the last 5 to 10 years, they have shown that they actually can do something that was not available before in any many-body context. So in these systems, you can actually take photos of many-body wave functions. And this is, of course, something which is completely new. From the information theoretic viewpoint, this is kind of a summary of what we know about quantum systems in terms of number of components and control. These are the two axes. And on the right-hand side, you have what they say, atomic limits, so systems where the number of components is of order 1, but you can control them very well. Think about metrology. On the opposite hand side, you have many-body systems, like in the solid states, where the number of components is very large, but the type of control and probe that you have is limited, typically by global response, what we know in the context of linear response theory. So these synthetic quantum systems, they are really something in the middle, in the sense that they have a number of components which is not macroscopic, but almost, so still already many-body. But at the same time, you can profit from single atom control and single atom probing. So this is really new. And in terms of mathematics, the corresponding mathematics, what you have is that every time you realize an experiment, you get a lot of photos, and in each of the photos, there is every possible spin that you are measuring at the same time. Now there is, of course, a question, because here we know how to characterize the system, so full density matrices, full state tomography. On the opposite hand side, you also know how to do it very well, typically local observables. So what can we do with these new observables that are now available? How can we handle such data sets? Okay, we need to have a theoretical framework to try to extract physically relevant information from such photos of a wave function. And this is exactly what I would like to show you today. Let me tell you what motivates us from the physics viewpoint. I mean, you can see similar motivation also from the information theoretic end side, but I would like to focus on physics. So this is an example of an experiment performed in a group of Emmanuel Bloch and Christian Gross, where what they realize is a Hubbard model in one dimension. Okay? And every time they take a photo, they see if at a given site there is a spin up, okay? This picture here, so where the red dots is, a spin down, blue dots, or no spins. In this specific type of systems, there are no double occupancies. And what, I mean, so you have in principle these full photos of data sets, and you transform them in strings. And so far, what people have done, they have said, okay, look, I have this fantastic string, but the only thing I can really focus on are few body observables. So they're actually extract low order correlation functions. So this, from the data science viewpoint, is a tremendous dimensional reduction. It's exactly a thing that you don't want to do. Of course, in terms of physics, in some cases, it is what we want to do because we want to extract a specific type of information, but we know that we are losing a lot of stuff in the process. Our goal is to lose nothing, okay? To really try to understand how the full information content relates to physics. And let me mention that this is, I mean, I'm coming to this topic from the condensed matter side, but you have very, very similar problem in high energy physics. I mean, and there the typical context is to try to understand topological phenomena. Similar example that maybe most of us are familiar with, phase transition in QCD as a function of temperature. It's very hard to understand it. And I mean, you would like, since even in that context, you have access to certain type of wave function snapshots in the form of path integrals, you can try to use some of this knowledge on the long run to understand also this phenomenon. Okay? And I would like to mention very interesting works in Jürgen Berger's and Biagio Lucchini's group that are exactly going into the same direction, but for different physical problems. Why do we want to do that? Let me give you a further couple of motivations. From the quantum information viewpoint, it is clear that at some point we will have to face analysis based on wave functions. And typical problems in this sort are verification problems. I mean, if you want to verify that two quantum computers are working, or you want to cross-certify them, it is pretty clear that looking at lower observable is actually almost meaningless, or it can just provide lower bounds. You want to have access to the wave function. You cannot do it exactly. This would be exponentially costly, so forget about doing tomographies or fidelities. You want to do it at the stochastic level, which is the only thing which is accessible. Okay? But you need a framework for that. You need a theory framework for that. Okay? These are some examples. And in terms of many body, there are different types of questions. I mean, in particular, what I like to focus on in this word complex. Okay, how complex is a system wave function? And here, I really mean complexity in a different sense that physicists are typically interested in. We are most of the time focusing on computational complexity, so which is the complexity of a task. Here, instead, we are talking about complexity of the data set. And this is exemplified by the quantity which is called Kolmogorov complexity. Kolmogorov complexity is essentially how easy is, given a string, given a type of information, to compress it. Okay? So the type of question that we want to ask is, can we compute the Kolmogorov complexity of a given many-body system, or even classical system? And can we relate the complexity to physical phenomena? So these are, of course, this cannot be done in general. Computing Kolmogorov complexity is undecidable. Okay, so it's clear that we will be able to do it only on certain type of systems, but that's the type of connection that we are interested in. Good. So the main idea I was mentioning before is to use data science, advanced statistical methods, and apply them to statistical mechanics. And the guiding principle in all of this will be to understand what the relevant degrees of freedoms that we know in physics are at play and how they actually influence data structures. Okay? In modern artificial intelligent language, we're interested in what is called manifold characterization. So a very, very primordial form of learning. I think even call it learning, it can be deceiving to some extent. Okay? And the applications that we have worked out so far, and I will not show all of them, they are mostly focusing on traditional many-body systems at equilibrium, critical behavior, topological effects. But we have also started looking at Floquet evolution, and including also application to both Rydberg and Kulkarni experiments. But today I will just focus on some of these. And if you're interested in the other, please let me know and I'm happy to discuss. Okay? Technical outline will be the following. First, I will present you what is one of the workhorses of my discussion, which is a concept in data mining, which is called intrinsic dimension. And I will just quickly focus on what it is, and then I will show you a simple example in terms of classical statistical mechanics, which shows how these concepts of data mining actually translate into physical properties. After this example, we will go to many body, and there the type of link that we would like to draw is the link between criticality and Kolmogorov complexity. And then after that, I will try to move to the connection between complexity and topology, okay, which is also different. And if time allows, I will also tell you a bit about these experiments on Rydberg quantum simulators. Okay. So what is the intrinsic dimension? Imagine that you have a data set and you want to describe it. The intrinsic dimension is defined as the minimal number of variables required to describe such data set. And here you can find two examples. The example on the left, here it's a set of points in 2 dimensions, so the embedding dimension is 2. But you can see that most of the points are actually aligned along a line. What does it mean? Is that if you know the variable x, you don't need to calculate the variable y. This is defined. I mean, this is automatically defined through a relation. Okay? So the intrinsic dimension here is 1. Here you see a slightly more complicated example. These are points distributed over a Klein bottle. So the relation is highly nonlinear. The embedding dimension is 3, but you just need 2 variables to describe the Klein bottle. Okay? Error. Okay, the dimensionality, so the definition of intrinsic dimension is true up to a given length scale. Okay, so in principle, if you want, I mean, the typical example that one has is that if you have points spread like this, if you look at the length scale, which is very short, then this looks like a 2-dimensional manifold. If you look at the larger length scale, you have 1D. This will impose us that we will have to find what is a physical length scale of our data set. And let me mention that this intrinsic dimension, we are definitely not the first that are using it in physics. I mean, there is a huge business in quantum chemistry, and in particular molecular science, interested in this. And there, the reasons are very different from ours, but I just want to mention that in terms of the methods to compute this stuff, we have not done any original work. This is essentially stealing stuff from other extremely successful communities. Okay? I mean, it is clear from these two simple examples that the intrinsic dimension is already telling us something about the data set. It's telling us how many degrees of freedom are there and how complex these manifolds are. But this is so far something which is very blurry. Okay? I'm not really defining complexity nor relevance in any strict sense. We're just seeing it by bare eye. And okay, there are many methods to compute this stuff once you have a data set. I'm not going to go into the methods. I just want to say that there are packages that you can go online and try to use. This DataPy is one example, and you can do computations very easily. Okay? Just to mention how to utilize these tools. Okay? Now, how do we connect this to physics? And this is our main question. And in order to do that, I would like to start with a very basic example. So a three-site spin model. Okay? Here, what I'm interested in is really try to sample the partition function of the spin model. This can be a Heisenberg model or a clock model. In this case, is Heisenberg. Okay? Nearest neighbor interaction. And the data space for this model is just three sites: θ1, θ2, θ3, three angles. Okay? And then what we do, we sample the partition function of this many body system according to just equilibrium weights. Okay, so the partition function. And we can do this simple experiment both at low temperature and high temperature. At low temperature, if we do that, we always sample states which have the same angle because the system is a ferromagnet. Okay? And if we try to portray the sampling in a configuration space, we will find that the only configurations allowed are the one where I have θ1 equal to θ2 equal to θ3. So this is just defining a line on our cube. Now we can try to do the same experiments at high temperature, and you already know what to expect. Essentially, at high temperature, we sample all states with equal probability. And this is what we find here, is that essentially the full cube is occupied. Okay? So from the data science viewpoint, the ferromagnet is something which has a very small intrinsic dimension. In this case, is 1. Instead, the paramagnet or the high temperature phase is something where the intrinsic dimension is 3. You will tell me, okay, fine, thank you, but this was a bit trivial. Okay? So can you show us a case where this intrinsic dimension is actually related fundamentally to correlation and is not just portraying in a trivial manner what we already know? If you want to do that, the regime where you have to go in classical StatMech is critical behavior. Okay, that's the best regime where you can check whether this quantity is really informative or if it's useless. Okay? And there are two intuitions that one can try to put forward. The first intuition is the following: is that you imagine a data space of a critical field theory or a critical model or a critical point. The correlation length diverges, so you can imagine, okay, then in data space I'm spanning a lot of points which are very diverse, so this intrinsic dimension will blow up. Okay? The complexity will blow up. But then there is the opposite intuition, which is RG. RG tells you that the criticality, if you give me a couple of numbers, you are able to describe exactly the configuration of the system, because the correlation functions are severely constrained, very strongly constrained by critical exponents. So who is correct? Okay? One predicts that this intrinsic dimension is maximum at the critical point, the other one is minimum. Well, so what we did a few things. First, numerical test, and then also some theory for that. Okay? And the results I would like to show you are for a very simple model, and later on we'll describe more complicated ones. The simple model is the two-dimensional Ising model. There's a conformal transition at a given critical temperature, 2.26, blah, 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 critical exponent 1. And the data structure is also something very simple. In the Ising spins, we can just represent them as zeros and ones. Okay? So what we do, we take our configuration that we sample from the Monte Carlo, and then in order to define a data space, we have to put a concept of distance into play. And the easiest way to do that for spin 1/2 is to take a Hamming distance. So essentially, given two configuration, we are counting the number of spins which differ. If you have configuration of this type, you see from S1 to S2, you are only changing one spin. From S3 to S2, you are changing 2. And from S3 to S1, you are changing 1. So the corresponding distances will be 2, 4, because we are multiplied by 2. Okay? Now, we do that, and that's the result. Okay? Here on the left, on the y-axis, we have the intrinsic dimension, which is essentially the complexity of the system. And here on the right axis, we have the temperature. And the different lines correspond to simulations, like classical Monte Carlo simulations at different system sizes from 40 to under 40 linear size. And what one can see here is the following, is that at very high temperature, the complexity becomes high, fine. This is essentially random. Low temperature, this gets low. But in the middle, there is a minimum. And the position of this minimum, which is denoted here by these yellow dots, scales towards the critical point as we increase system size. Okay? So this is supporting this RG intuition that complexity at critical points is minimal. And in order to really show a relation between this complexity and criticality, of course, just looking at the picture is not sufficient. We have to somehow satisfy some form of universal scaling behavior. And this is what is shown here. What we are doing essentially RG on this intrinsic dimension. And this is the result of what is so-called collapse plot. Essentially, what we are assuming is that there is a universal scaling function, which is just related to the correlation length, so it's sensitive to the critical exponent nu, up to some size correction L. Okay? And the quality of this fit is a kind of a demonstration that this intrinsic dimension is universal, which is somehow extremely bizarre because it implies that the system, the Ising model, has a transition in real space, which is given by its critical exponents, and there is a corresponding transition, which is a structural transition in data space, which has, it appears at the same critical point and also has the same critical exponent nu at least. Okay? The other ones we cannot compute. Okay? And also the critical temperature is very close. Okay? So this, I think, the main message is that at the level of classical StatMech, there is a deep connection between this intrinsic dimension, between these concepts from data mining and many body effects, okay, and correlations. Why is this happening? This is, of course, a very legitimate question. And the idea is that these data structures, they are somehow related to arbitrary body correlation functions. Okay? So this implies that they are essentially dominated by the most relevant correlation function. So if the most relevant correlation function is 2-body, they will be dominated by that. If it's 4-body, they will be dominated by that. If it's a Wilson loop, they will be dominated by the Wilson loop. We are not inputting any information, they automatically extract the relevant one. And if one does a bit of analytics through this cumulative expansion, one finds out that close to critical points, this intrinsic dimension scales like a constant plus 1 over xi, which is demonstrating analytically this minimum feature that we have shown below, and also why this intrinsic dimension at finite size is actually giving us, is sensitive to the critical exponent nu, which is the one related to the correlation. Now, fine, you can tell me, but so far it was classical h bar equal to 0. Maybe I'm not interested. I'm personally very interested, but I think there are different viewpoints. Then the question is, can we connect this algorithm complexity to physics in other contexts? Okay, and yeah, please. Yes. Okay, this one, zeta. This is an interesting question. Okay, zeta is an exponent which is operator dependent when you do finite size scaling. Essentially, if you want to know this ab initio, you will need to relate ID to a specific operator of your Ising field theory, which is something we are not able to do. Okay. Actually, for Ising field theory, this is corresponding to no other exponent. But you know, when you do finite size scaling, imagine that you have an operator which is a composition of 2 relevant ones. You will see a number, and I think this is signaling us that ID is actually related to more than one relevant field. So, okay, that's why it's happening. So, and I think the 2 directions where we have tried to expand this are quantum, so path integrals, and topological effects in classical StatMech. Let me try to tell you something about these topological effects, because I think for the theory is more interesting. And then for the quantum side, I will immediately jump to experiments and I will tell you what happens there. So complexity and topology, I mean, 2 kind of concepts and 2 that are very useful in physics. But then the question is, are they connected? So can we diagnose a topological phenomenon through complexity, through algorithmic complexity, not computational complexity, or vice versa? If I have a given complexity, can I see whether the phenomenon is topological? And what we did the following. We studied in classical stat-mech, the Berezinskii-Kosterlitz-Thouless mechanism. I mean, it's not the only topological effects in classical stat-mech, but is the one which is, in my opinion, is the most elegant. And the idea in concrete is the following. We take a two-dimensional classical XY model, and then we study its phase diagram. Its phase diagram, we know on the square lattice, we know supports two phases. At very high temperature, the system is trivial, is decorrelated, is a paramagnet. But then when we go below a critical temperature, TC, we cannot have true long-range order because of Mermin-Wagner, but there is still a ferromagnetic phase where the correlations are decaying as powers, power laws. And here the physical picture behind BKT is that below TC, the basic excitation in the system are vortices and anti-vortices, and there is a law that determines how the two interact, and the law is given by just Coulomb equation in 2 dimensions, which is a logarithmic repulsion. Okay? But the key point is that these vortices, these basic excitations, have topological origin. Yeah? So you can essentially label them through winding numbers. And what we did something very straight, and this is motivated by topological field theory. So what we do in topological field theory, essentially, you enter a manifold to get a number, get an invariant. So here we were doing the following. We take the XY model, and then we compute this partition function on different manifolds. You can do torus with 1 hole, torus with 2 holes, Klein bottle, Möbius strip, blah, blah, blah. I mean, of course, we realized that nobody has ever studied the XY model on a Klein bottle, probably for good reasons, okay? So it was not so easy to benchmark this computation, but I mean, this can be done, and one can utilize, on most of the cases, very, very efficient and known algorithms. And then we computed the complexity of the partition function on a given topology. And these are the results of this Monte Carlo simulation. On the top, here we see the complexity as a function of temperature for the case of G tori. So toris with a given number of holes, 1, 2, 3, 4. We have done up to 12. Okay? After that, our coding and trying to understand how to put the torus on the square was a bit too complicated. Okay? And actually, finite size effects become too strong. And here one can see the following. If you go to high temperature, so here the transition point is around 0.9, but at finite size, since a BKT, you can see critical effects up to larger values. So this point is representative of high temperature. At high temperature, the intrinsic dimension essentially is topology independent, which makes sense. If I look at a system which is not correlated, if it's on a torus with 1, 2, or 3 holes, there will be no difference in the data structure indeed. However, if you go to low temperatures, below the BKT phase, the different topologies actually have very different intrinsic dimension. And what is interesting is that the larger the number of holes, so if you want the larger the genus, the less complex the partition function is. That's an observation. Yes, please. Sorry? In configuration space, we use Euclidean distance. Yeah. For reasons which, I mean, it's not once you use Euclidean distance for this kind of computations. So this is a first statement. And then we said, okay, fine, but these are all relatively simple manifolds. Let's go to something which is really complicated, like non-orientable and so on and so forth. And these are the results that you can find here. Okay, same stuff, intrinsic dimension as a function of temperature, same system size, 72 square. And here what you can find are different things. Oh, I'm sorry, these are not defined. So RPP is the real projective plane. Klein is the Klein bottle. Torus is the torus with 1 hole, and then cylinder as Möbius. Forget about the moment about cylinder and Möbius, because these are manifolds which have actually boundaries. Okay, so the role of the boundary can be tricky. RPP, Klein, and torus, they're all closed manifolds, and they're all very different from each other. At least within our error bars, we can easily distinguish their complexities. Okay? So the message is the following. Above TC, complexity is something which is topology independent. Okay? So in general, there is no relation between topology and complexity. But if you enter the BKT phase, there is. Okay? And topology determines complexity. Yes, please. Yes. Yeah, they're all the same there. They're all the same. Within error bars, you can also crunch numbers and make the error bars very small, and they're still within our error bars. So there is no way we can distinguish. Yes. No, the partition function, you cannot contract the boundary. I mean, the partition function is defined on a manifold, and there is no way you can contract the manifold. There is no continuity in that sense. Let me also say that, of course, the first thing we have done, we have tried this for the Ising model, which has no topology. Okay? And the Ising model, the intrinsic dimension is always within error bars for arbitrary points. Okay? Now, how is this connected to topology? I mean, in order to do that, we did the following. We computed the intrinsic dimension difference as a function of sampling, because you can say, okay, you're sampling this partition function in a finite number of ways. In your experiments, this will be maybe 1,000 to tens of thousands. In our Monte Carlo, we can do slightly better, but not much more. But the question is, if this intrinsic dimension changes as a function of your sampling, the thing that you're seeing in terms of the influence of topology and complexity, this is kind of a strange artifact. Okay. Well, here you see the results of the intrinsic dimension difference with respect to the torus of genus 1 in absolute value as a function of sampling. And within error bars, one can see that they are, I mean, the error bars here will be roughly 10%. These quantities are sampling independent. But what is even more important is which complexities are really the ones which are close to each other. And here I've written this equation, is that the complexity of the torus, in our case, is equal to the complexity of the Möbius strip, of the Klein bottle. And then you'll tell me, this looks bizarre. Because if we think about the Klein bottle, this is genus 2. So I was expecting this to have the same complexity of a manifold with genus 2, torus with 2 holes. Of course, this is not true. Okay? And the point is that it is not the genus of a manifold that determines the complexity, but it's actually the dimension of the abelianization of the homotopy group, the homology group, essentially. Okay? And one can make it more concrete. And of course, if you look at the torus and the Klein bottle, the dimension of the homology group is the same. It's not the Betti number, because in one case there is a discrete part, but the dimension is the same. So essentially what it's telling us is that the complexity of our partition function is sensitive to the proper labeling of excitations in the system, which we have not inputted in our computation. It's just coming out automatically. Of course, this is just the XY model. It's a simple model where we know how to label them also analytically, but imagine to do that for an SU3 gauge theory, where the nature of the monopoles, it is not known, okay, or not established. This would be a way of doing that. Now, so far, okay, a few minutes. I would like to show you just something which is quantum, because so far has been theory, has been classical StatMech. We have done, for the critical behavior, we've done same thing also for the quantum. And idealized conditions, so closed systems, huge sampling, blah, blah, blah. Okay. What about experiment? Yes, please.
A bit of a continuation. Are these results robust to which metric you use?
Yes, they are very robust. This difference, I mean, as long as the metric is Euclidean type, they are robust. If you put a metric which is not Euclidean, then I don't know what happens. Okay, but also it makes not, to me, it doesn't make much sense to study non-Euclidean metrics in this context, because they are not sensitive to correlation. So what about experiments? And here we did two things. We analyzed, so we wrote essentially pipeline to analyze lattice experiments, and we analyzed this experiment by the group of Antoine Brevet, Rydberg atoms in optical tweezers. And we also have a pipeline to analyze experiments in the continuum. And in this context, we analyze the dynamics of spin or Bose gases. Let me focus for the sake of time on the first one. Just give a brief introduction. In this Rydberg atoms array, what is happening? So people have atoms that are in the ground states, for instance, rubidium atoms, and then they shine light, which is quasi-resonant to a Rydberg state. A Rydberg state, you can imagine, is a nucleus with electrons traveling at several nanometers distance, so it's a huge dipole. And the effective dynamics described in this stuff is something which is an Ising model with transverse and longitudinal field. And the interactions, they are actually not necessarily nearest neighbor, they decay like 1/r⁶ in most of these experiments. Okay? This is the type of modeling that we require. And what these guys did in the experiments, they start from a paramagnet, so a state where the atoms are always in the ground state, if you want all the spin down. And then, by changing both the transverse field, the longitudinal field, and the interaction, they enter a ferromagnetic phase, which in the terms of atom density is equivalent to a charge density wave, 0, 1, 0, 1, 0, 1. This is perfect for us because these are binary data sets where we can apply all the toolbox that we know from our classical StatMech understanding. But of course, this is different context. Here, nothing is at equilibrium. We are far of equilibrium. We are doing essentially a Kibble-Zurek type experiment. So this is the analysis. And the motivation for us to look at this specific experiment is because it was something where we could understand whether there is really an interplay between complexity and criticality under these non-ideal conditions. Okay? We also did something which is related to network theory, but I will not be discussing it here. And these are the results that we got. I mean, this is the intrinsic dimension as a function of the time along the experiment, where we compare the experimental data, which are these black points here, and variational simulation, variational Monte Carlo simulations here in these red dots. And one can see here there are two regimes. So there is a first regime at short times where complexity actually shoots up, increases like crazy. Okay? And this is not particularly relevant for us. It's just the onset of quantum fluctuations. And then there is another regime, which is this blue one, which is the regime along which the transition is really crossed, the Kibble-Zurek regime, where the complexity scales monotonously with time and decreases. So this implies that there is a kind of, there is a universal behavior here in terms of complexity monotonously decreasing. Then you tell me, okay, but this is opposite of what you have seen in classical StatMech. In classical StatMech, you found just a minimum of complexity at the critical point. It is true, but this is because it was equilibrium. Actually, if you do the analytics correctly, what you find out is that in the context of this Kibble-Zurek, complexity is dominated by the correlation length in the very same manner that it was in the classical StatMech, and across Kibble-Zurek, correlation length keeps increasing as a function of time. Okay? So this is essentially telling us that the data space becomes more and more constrained, so its complexity is decreasing. And these are for two different system sizes, L equal to 8 and 10, square lattice, and they give essentially the same results at the qualitative level. So this is an observation of emergent simplicity that we are not aware of has been observed in other contexts. Yeah? Good. So what we learned and what is next? I think what I've tried to convince you about is that stochastic sampling of wave function is interesting. So even if we are unable to get the full wave function, there is still a lot of information that we can extract from that with methods that are controlled, that goes well beyond what two simple body observable can tell us. Complexity and criticality are deeply connected, at least in classical StatMech. I think we have analytical proof, and in quantum one, we have numerical evidence. Complexity and topology are also connected. Again, classical StatMech. Quantum is a different regime here. We don't know if there is a deep connection. And we have also, I mean, this is something which was related to the experiments, that some of these tools can also teach us something about how these machines, these quantum simulators and quantum computers works, but I've not discussed this. Just if you're interested, I can tell you about that. Of course, there are a lot of open questions in quantum. I mean, this connection between topology and complexity, this we don't know anything at the moment. Out of equilibrium, kind of tricky in the sense that, again, it's very hard to write down these theories. This connection between data sets and the physical properties in that context. And of course, there is the challenge when you have quantum mechanics that you can start, of course, analyze path integrals, but there are also fixed basis measurements, which are the one relevant for experiments. And understanding the role of basis in this context is also something which is partially open. Okay, with that, let me thank the people that really did the work, in particular Alex, Adriano, Vittorio, and Tiago, and for the new staff also Roberto and Rajat and all the other people, and thank you for your attention.
Thanks, Marcello, for the presentation. We have time for questions. Please, Marin.
The first question is about the quantum experiments and the quantum results. So when you have quantum data, one way it differs from classical data is that you can also take quantum measurements in different bases. Yeah, now, when you do this, of course, there are correlations between that. So do you see, or what is the effect for the intrinsic dimension of these additional freedom?
Okay. In the context of these experiments, I cannot answer your question because the only data sets that we had were in the Z basis. Also because in Rydberg, it's actually not easy to make a rotation locally, since there is Rydberg interaction there. If you do a rotation, the system still interacts, so it's hard. What I can tell you is that in one dimension, we have done a study of this. And what we found out is actually that if you look at a single basis, you can only understand very simple phenomena, okay, like symmetry breaking, like in the classical case. So for instance, you will not be able to see SPTs. If you combine different bases, you can actually have a network-based classification of phases of matter, where your SPTs behave differently from critical behaviors, conformal critical behavior, symmetry breaking, and so on and so forth. You need really all the bases. So the short answer is, it's important to look at different bases. In this specific example, it was not needed.
Okay. And the first question was about the intrinsic dimension itself, also like classically. So in some sense, I don't know if my intuition is true, but it looks like you are trying to make a statement about the distribution that generates your data, right?
Oh, yeah, yeah,
through this.
Sure.
And now I know that you've
this.
mentioned in the beginning, you don't want to talk about, parameterizing these distributions in any way, but can you basically make a statement from your, analysis that the distribution essentially simplifies at the critical point and is much more complicated away from the critical point?
This is correct. This is fundamentally correct.
Right.
I mean, to be honest, this connection between Kolmogorov complexity and critical behavior in classical StatMech, people have talked about this. I mean, there is a beautiful, I don't have paper reference, but there is a beautiful YouTube video of Sean Carroll. And when he describes critical behavior, he just says, this is a minimization of Kolmogorov complexity. And essentially what we are doing is that. Okay? Just we have tools to compute this, which in general is very hard.
Yeah, so thank you for this interesting talk. So my question is maybe a bit more, I don't know, soft. So is complexity, it seems so that you can distinguish these topologies in different way below critical. It seems unusual. Is complexity unique measure in this sense, or?
No. I mean, first of all, if you want to spot the position of the critical point in the XY model, you use the winding numbers. You use something which is not the complexity. Okay?
No, I don't mean the position of the critical. I mean distinguishing the topologies below critical.
No, I mean, again, there you can also use winding numbers. I mean, if you know your phenomenon, you don't need to use complexity. Complexity is good, in my opinion, because it's assumption free. So for phenomena where you have no idea about what's happening, then this tool can really be informed.
Yeah, this I mean.
Yeah, no, that's my statement. Yeah.
Thank you.
Cheers.
Have you considered what would happen if you looked not just at snapshots at one time, but the time trajectory, and whether there's anything extra there if you look at the time evolution of states as well as the snapshots? We have done it only in one context, which is the context of what is called non-equilibrium fixed points. This is experiments by Marcus Oberthaler. There, in this non-equilibrium fixed points, essentially you have a collapse in the scaling function of correlation functions which are time and space dependent. And then the question is the complexity of your data set simplifies when you take the data set in time and space? We have observed this, but for these specific statements, I think our statistics are not enough to say, okay, the complexity is minimal. We just don't have enough statistics. What we observe there instead is that the complexity along this universal window is actually time independent. This is a statement we can make. If you're interested, I can tell you more.
Yeah, can you use this to benchmark the quality of approximations? So if you sample—
Sorry, the quality of?
Approximations. So if instead of using the exact sampling, you would try to do min-field or other methods, would that help like quantify which approximations are better, which are worse, and maybe even shape them?
You can do it in the cases where this intrinsic dimension has a connection to the state that you are looking at. For instance, I mean, there has been a huge discussion in the recent years about neural network quantum states. And one example of these neural network quantum states are autoencoders. In autoencoders, I'm sorry if I get technical, but I'll just say shortly. In autoencoders, the intrinsic dimension, it is a very well understood parameters in the sense of the parameters of what is called a bottleneck. Okay? If you want to represent a state which has highly non-trivial correlation in terms of intrinsic dimension, you already know that your approximation, as long as your autoencoder doesn't have a sufficiently large bottleneck, will fail. So in that context, I can make a precise study of efficiency of a method with this with these quantities. For other methods, I do not know. One first needs to understand analytically what the connection is with simple cases. And
a rather specific question about the Kibble-Zurek. Do you mind going to that slide?
sure. This or
the following? Yeah. So this graph that goes up and then down. So where is the transition happening, roughly speaking?
Okay, the transition happening between 3 and 4.
Between 3 and 4.
Okay, I don't. Okay, actually, I should remember the right number. But the point is, we ask explicitly experimentalists not to tell us anything, because when we do this analysis, it's better to be blind. But just, I mean, the number is between 3 and 4.
So it's already decreasing by that time.
Yes, because this is an important point. The decrease starts when the Kibble-Zurek region starts.
The non-adiabatic. And so you start creating excitations. Correct. And the complexity goes up. Correct. And when it starts decreasing, then it's coarsening, or it's still in the non-adiabatic regime. It's
no, when it starts increasing again, you mean?
Yes, yeah. When it's decreasing around 4 and 5, is it?
No,
we're still in the non-adiabatic regime.
You mean here?
Yeah.
Yeah, here we're still in a non-adiabatic regime. The point is, you see, there is a plateau here. And I think the presence of these plateaus, at least in the experimental data, is due to the fact that at some point you get sensitive to noise because the system is open here. Okay? And in particular, for these experiments, the decay rate, it's roughly of the order of a kilohertz. It's a bit smaller, but it's a fraction of a kilohertz. So you expect that after 5 microseconds, actually something starts happening. But no, sorry. It's actually tens of kilohertz. I was correct. Okay, so around 10 microseconds, you start feeling the effect because it's 100 atoms. And of course, when dissipation kicks in, the complexity shoots up because essentially complexity here is a measure of randomness, and dissipation will make the system.